There's like just
I mean, I'm not gonna complain because everybody can get away from me. Just kind of back in.
just run in here.
Just
hide through the classes. I see you. All right.
I gotta always come up with somebody else who's in this class. So I can't get in here by this.
All right. Yeah. So the next half an hour or so is just going to be kind of walking through, kind of more or less just observing the heap in action. Like I said, there's some things about it that can definitely mess up exploits, and it's just things that you have to keep in mind, especially the auto coalescing can really get like annoying sometimes. But yeah, so let's walk through it really quickly. That's not a C file. Yeah, no problem. All right, so we have 3 allocations being made. We print out their addresses. In this case, then I'm freeing the first and the last. Pause for a second, free the middle one, and I realize I should also. Oh yes, good point. Did I click the record? I did. All right. Yes, we are recording them. So. Yeah, so like I said, because of coalescing, basically nothing will happen with A and C, right? They'll stay as they were when they were freed. However, when we go to free B down here, all of these allocations are just going to get mushed into a single allocation. And so we'll see this, and then I'll modify a little bit to show that this is really one big allocation on the list now. So let's build it really quickly. So, GDB. All right, so you can see we run it. Another thing to note, and I believe I mentioned this before, is even though we were allocating size 20, you can see these are obviously separated by hex 30 bytes. So what's there? You'll notice also just sort of tangentially related. GDB does very nicely show us, label this heap, and with GDB, I believe the heap always ends up immediately after the program, like the end of the program's allocations. Again, as we saw earlier, this is not true outside of GDB when ASLR is enabled, but inside of GDB, keep things nice. It should just end up right around there. But let's look at memory and see what we actually have. Because again, we have the allocations are separated by size 30, and this one is offset by 10. So what gives? You can see right now there's not a whole lot, and I guess let me actually change this really quickly to make it a little bit more obvious. So we'll just star copy A into A, and B, and C, and C. All right. So there we go. So now this is a little bit more obvious where the allocation bases are and what's metadata. So again, the first hex 10 bytes before the allocations are what's known as heap metadata. In this case, since the allocations are in use, this is 0. I don't believe the value actually matters here. And notably, this is hex 31. That is essentially saying the size of the allocation is the upper hex 30. And then this is the low 1 bit. This is more aptly looked at as a bit mask. Actually, the 1 basically just means this is in use. This is the previous in use bit. And so if we continue, we've now freed A and C. Again, so in this case, though, you can actually see these things were overwritten. However, it's not like these zeros, if we were to look at them, wouldn't actually be. This is overwritten because of how the heap is linked together, more or less, how the allocations are kept track of. You'll see down here we've actually magically gotten the address of the base of the heap, because this is actually a pointer from C's block allocation to the beginning of the previous allocation, which was A, right? This is a pointer to the previous allocation that has been freed, which was A. A does not have a previous, and so you can see this is changed definitely, but again, these zeros actually would not have been changed if I had filled them in. So if we continue once more, when V gets freed, you'll notice everything should look a bit different. Things are now pointing around in weird ways, and more importantly, if we look at this as, if we actually modify this to do another allocation here, so if we now malloc a new larger section, size hex 40, if I'm not mistaken, this should end up at the same place as A, because everything gets coalesced down into the place where A used to live. That is not the character I want. Oh, right, these are too small. Yeah, let's make these Let's make this a little bit bigger. Yeah, so the point Danny just made, we will talk about a bit. We may talk about it next week. We will see. That should work. Let's make that 180. No, let's make that 380. Okay, so we can all definitely agree that an allocation of size hex 380 would not fit into the same allocation as a hex 200 allocation unless things were being coalesced. So let's see. Good. So you can see things were coalesced back down, right? D now is A's address because they were all freed. This is where exploits that use after free stuff have to be really careful, because if you free the wrong thing, you can collapse an entire chunk of memory down, and now all your allocations are going to start back at the beginning. And if you can sort of force, if you can control how large an allocation is, you can almost force where it's going to land based off of the existing free list and seeing if it could fit in a prior allocation. However, it can get kind of tricky when you're keep track of what the state of everything is in. At a really high level, let me try and explain the point that Danny just made so that there will be people will sort of understand why these sizes are the way they are. So for optimization, the way the default malloc works on Linux and OS X and I believe basically everything else is it has multiple sizes of chunks that it can allocate. So you have really, really tiny chunks, which are under, I believe, 80 decimal bytes, or is it hex? I think it's 80 decimal bytes. And those are called, those get put into a separate thing called the fast bin, or the fast, how do I put this? They're stored separately because they're super small allocations, and the theory is if you're doing a lot of malloc-free, 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 you're going to be probably working with smaller amounts of data. Right, you aren't expecting it to do, many kilobytes or megabytes of an allocation, free that immediately, and then give you back the same thing. So these are stored separately. So because of that, you can do weird things can happen. So for instance, if we do change these back to be of size 20, and then make this an allocation of size hex 40, let's say. This should behave differently, even though the base theory is correct. And you can see it does. It completely changes. The allocation is now somewhere really, it's way out in memory, completely away from where A, B, and C were, even though we had 3 hex 20 allocations and a hex 40 allocation. Assuming I remember the fastbin size correct, that's probably because the hex 40 is over. No, that's actually, let's try decimal 40. Just make sure. Yeah. So regardless, things ended up at a completely different place, and this is like the fastbin in action. This does not work the way it does with other allocation sizes. So we set this back to hex 400 and hex 200, hex 200, hex 200, and we rebuild, rerun. We should be, so we're back to how we were, where things, this makes sense on paper. This makes the most sense on paper compared to all of the other allocation strategies. So that's, coalescing is one thing that is probably the most important to keep in mind when you're doing like UAF like exploitation. One of the most common CTF challenges based around this is you have the famous 4-option menu and you're writing notes. So you have a note structure, you say how big your note is, you write that much into memory, you get an allocation of that much size, you read your data into it, and then you have a way to edit a note and delete a note. So another thing to note is, unintentional, I'm sorry. Let's make these allocations a little bit smaller. If we make that size, let's say hex 18. So we're making that size for a very particular reason. If we now fill up this buffer, this allocation with hex 18As, which I don't want to try and count out, so let's just Python it away. And don't think we should need any freeze for this. If we now printf a, there is the potential for something weird to happen here. This comes down to how C strings work, right? They're null terminated. And you can see up here, I didn't copy, there's no null terminator. And actually, let's just be safe, make that a mem copy. What's this index in industrial zone? Okay, so if we copy over exactly hex 18 bytes, if this works, we may have to change things up a little bit. Malloc and malloc. Yes, it did work. There's a 1 there. If we run this again and look at the heap, just grab from A. So what's happening here is that, and the reason I chose this hex 18 is because the heap, because it needs metadata at the beginning, is going to hand you back an allocation where basically the next, how do I say this? The metadata of the next allocation is going to start immediately after the end of the prior allocation's data at an offset like +8 in this case. And usually, because of how the heap works, the allocations you get back will always be aligned to 16. The metadata will be just before it. So what we're doing here is we're filling up the buffer that we control with A's. And then this 3.1 is actually the metadata for the next allocation. This is a very common issue, and the issue itself is made a lot worse because of how you can groom the heap, which is the grooming the heap is the name in general for figuring out the correct order of allocations, frees, reallocations of different sizes, and just in general setting up the heap to be how you want. So in this case, if we can find a way to make this the heap address, if we can find a way to make this be the address of, say like the previous free entry, as we saw happened earlier, and then we print out this item, we can now leak a heap pointer. And again, heaps are normally, you normally have ASLR enabled, so we've now defeated ASLR, right, by just leaking the heap pointer. We know an absolute address where the heap lives. So let's see if I can type. So like I said, you should in theory see actually let me change this. So you should in theory see you should get a heap pointer immediately adjacent to the prior data section, to the prior data part of the allocation, when you have a when you have two things that are freed, like we'll free A and C in this case, and C should get its previous pointer set back to A. So we're going to memcopy into B this time. We don't even care about addresses anymore. Let's assume that we don't get those for free. And now we're going to free A and free C. If I did this right, when we run malloc now, interesting. We've definitely corrupted something. In this case, that doesn't even quite make sense because we should. Oh yeah, because I'm printing A. That would make a little bit more sense. Let's. Do I have this open in two places? I do. Okay. /malloc. Aha. We have successfully leaked some data. So let's run this under debugger to see, maybe a little bit more detail what exactly is going on. Again, we can use info-proc map, find the heap section, and let's just look at a lot of addresses there. And you can see, perfect. Here's our allocation that we're printing out. And here's a heap address. Actually, that doesn't quite make sense how that's lining up. I see what's happening. Okay, regardless. We have the heap address here. Another thing you'll notice is these. If we look up here a little bit, you'll notice these point into libc. So again, because of how some of the details of how malloc and free work, you will also get pointers into libc, depending on how the heap is set up. You'll get pointers into this main arena thing. We may discuss what this is about next week, we'll see. Regardless, you also have the opportunity to leak libc pointers, in addition to leaking heap pointers, which is a big win, right? We can now, in theory, just leak libc by creating some allocations in the right order, assuming whatever method is being used to read in our data, if we can then edit it, if we can then see it, we have the 4-option menu is usually new, print, edit, delete. If we can print out the thing and we've groomed the heap correctly, we might just be able to print out a libc address. This is great. We don't need an arbitrary read or something. We don't need to pivot around. We can now just get libc out and start using it. This is a super useful thing about the heap. It gives you pointers to itself, gives you pointers into libc if you set it up right. So I realize here, like I said, the actual data that was leaked here, if we put that in XXD, yeah, so you can see this is the 411 that we have up here, not the actual libc pointer. Grooming the heap for this kind of stuff, even like it's a trick. Honestly, a lot of the time the best thing to do is just like mess around in a simple example like this. Replicate what you have control over, and then just start messing around and seeing what you can create. So in this case, it looks like this should be the previous pointer, but what happens if we can create another allocation immediately after C? Let's try also adding it to the list of things that we free. And run malloc. So that's still the same. Perhaps we need to cycle the order around and do it backwards. No, that's still the same. So there's a lot of, you can spend the time to learn how this works. To be honest, it's usually easier just to kind of mess around with stuff until it does work. The heap, especially, it changes a lot. Danny and I were actually just talking about this over break. If you find documentation, I would say before like 2011 or 2012-ish, it's probably wrong. Because pretty consistently there have been changes, especially in free, to make sure that you can't use it to get an arbitrary like write what where primitive. This kind of just like butting up against the next allocation, that's kind of hard to just avoid. In theory, they could always add some null padding between, but that's just burnt space. So this is kind of like the easiest type of using the heap for malicious intent, if you will, and it is quite the beast to try and figure out. You know, I know that there's a way to get this to work to leak the pointer. I forget what order you have to free stuff in, and again, because of how small allocations work, the order in which you free stuff does matter. Things get pointed around differently. You know, perhaps we need another allocation in between these two that wasn't freed. Let's try that. Okay, so now there's a 3-1 there instead of a 4-1-1, right? You know, so little things like that can make a big difference to what you get out. The homework will probably not be based around this. We're going to go into a bit more detail with this next week, and hopefully I'll have some, you know, formally prepared examples where I can be like, oh look, a libc pointer has appeared. But for now, just kind of know that there is a lot of weird stuff that can go on with even little things like forgetting to null terminate a string in like a notepad like app or something like that. So yeah, that's kind of what I wanted to talk about with heap stuff today. I didn't want to get into a whole lot more, but before we go, I've been working on something the last couple days, which I almost just wanted to show off as like enticing people to come into the lab and work with us because you get cool tooling. So you know how, well, especially, whoops.